Today we have several things to do. So first, I want to finish just lasso and rich regression part of chapter 6. So chapter 6 is a long chapter, so it includes the lasso rich regression and also the principal component analysis and also the regression in high dimensions. So we just want to finish the 6.2 rich and lasso regression first. Then we go to the lab session. So chapter 6 have several lab sessions, but we will cover the rich regression and lasso part. So that is lab 2. The slides are available. Then after that, hopefully we do some exercise today for rich and lasso. So the point is chapter 6 is a long chapter. So after rich and lasso, that we do lab session and the exercise. And yeah, first, I think I have to share the screen and and the midterm, probably I will be assigning maybe today or tomorrow, and will be due next Friday. I mean, not this Friday. And probably you will have 3 questions. And one is very practical problem to predict something. And the other 2 are similar to the homework. Okay. So last time that we studied lasso and rich regression, maybe we review it first. So we are thinking about basically the usual linear regression, but we want to have a different way to optimize these parameters. So that means that sometimes the linear regression have too many large coefficients. So we want to restrict the size of coefficient, or we want to restrict this the number of non-zero coefficients. And we discuss first the rich regression. And rich regression, the algorithm is here. So in linear regression at first, we minimize the residual sum of sum of squares. But the rich regression minimize the RSS plus this lambda times summation of beta j square. So beta j squares, so these are coefficients in a linear model, and the lambda is some constant. So I would say just predetermined constant. And we want to minimize this entire quantity. So we have to minimize RSS, the sum of squared residuals, and plus constant times the size of coefficients, a kind of size of coefficients, summation of beta j square. So it balances the size of errors and also the model complexity. So simpler model is better, and also smaller RSS is better. And lambda will be determined finally by cross-validation. It's called tuning parameter. So it's a kind of the nuisance parameter. So beta j is the parameters of interest, but the lambda is a kind of intermediate parameter. And another method we discussed is lasso. So lasso minimizes this quantity. So RSS plus lambda times summation of absolute value of beta j. So only this term is different from rich regression. So the idea is similar. So we want to have smaller RSS, but also the total smaller sum of the absolute value of coefficient. And Rich and Lasso are similar, just the penalty on beta are different, whether beta absolute value or the beta square absolute value. And beta, what's the difference in characteristics? So beta absolute value is much larger than beta square absolute value if beta is small. For example, beta is equal to 0.01. The beta square is equal to 0.0001. So basically, the rich regression does not penalize the small parameters. So usually all betas remain non-zero. I think that as long as in linear regression, usual least square gives non-zero beta, then rich regression also gives non-zero beta. And yeah, unless every beta is equal to 0, lambda is equal to infinity, that's possible. But except for that, the non-zero beta remains non-zero. But the Lasso regression, the size of penalty is pretty large. So for small beta, so beta is actually pretty small in least square estimate, then actually in Lasso regression, the beta becomes 0, so shrinks to 0. So that's the one big difference. Yeah, and this is another formulation of Lasso and rich regression. So in the original definition of Lasso and rich, that we minimize RSS plus lambda times something. But these parameters, beta naught to beta p, those are obtained by this method also. So the parameter estimates of Lasso can be obtained by minimizing the RSS subject to this criterion. So the summation of the absolute value of beta j is less than s, with s is here constant. So the solving this optimization problem is equivalent to solving the Lasso, I mean the estimating Lasso with some lambda. So we have some corresponding between the s and lambda. So large lambda means larger penalty, so that means the small s. And the small lambda corresponds to large s. So we don't have any specific formula to see this correspondence, but the Lasso solution, Lasso estimation for specific lambda, say lambda naught, corresponds to this optimization problem with some s naught. So that is the property. Yeah. So we are not discussing optimization procedure, so we don't prove it, but we have some correspondence. So if you estimate Lasso model with original definition, then we can get all coefficients, right? So then we can identify S naught. And the other way around may not be true, but once you know lambda, you can also get S. Yeah. And actually, probably in estimation algorithm, the solving this, question, this problem is easier than this, optimizing the parameters with original definition of Lasso. And rich regression also similar. So the constraint is replaced by summation of beta j square is less than s. So it's similar. So you can see that this is the diamond basically on a plane on a space of beta 1, beta 2 up to beta p. So usually the intercept is excluded. So intercept excluded. And here, the summation of beta j square is less than s. That is basically within the circle or within the hypersphere in a space of beta 1 to beta p. So this is two-dimensional case. So we are searching the solution within this range that is equivalent to lasso. Within this range, it corresponds to rich regression. So with this equivalency, basically the lasso and rich are doing this. So at first, this is basically the restriction. So we are thinking about lasso here. So this is a restriction in the parameter. So the parameter should be within the square, within this square. And this is the contour plot of RSS or likelihood. So contour RSS. So here RSS is smallest. And getting larger and larger. And you can see if this contour that touched this square, then that point is optimal solution, because outside of this range, actually the RSS is larger. And our objective is minimizing RSS with this restriction of parameter. Given that parameter is within this square, that we want to minimize the RSS. So this is optimal point. And in this case, this optimal point is beta 1 equal to 0 and beta 2 equal to maybe S. Of course, sometimes the contour is like this and it touches here. So beta 1 and beta 2 are not 0. Both beta 1 and beta 2 are not 0. But in this figure, the optimal point is here. So beta 1 is 0 and beta 2 is S. And here, the rich regression, the same thing, just restriction is circular. So remember that the beta j square summation, this is less than S. This is the condition. So maybe here square root of S, negative square root of S. Then, and this is again the contour of RSS. So this is the optimal point. So in the left-hand side, actually, many of the times, this optimal solution has the many zeros. I cannot really prove it, but you can imagine that in many of this contour plot, this intersection of basically the smallest contour and the square is just on the vertex. But the circle is uniform shape, so no reason to believe that this point is more likely than this point. So this is one explanation. I mean, another explanation that the lasso has more zero parameters. So more estimated parameters equal to 0. More estimated parameters are equal to 0. So the lasso tends to give a simple model that since more parameter estimates becomes 0. Simpler in the sense that we have less non-zero parameters. So in general, we cannot say whether lasso or rich regression is better in prediction. So lasso works better if the true model has a few non-zero parameters. Rich regression works better if the true model has many non-zero but small parameters. Maybe practically, we want to use a model with fewer number of predictors. Maybe that is practically easier. We have to prepare the less number of variables to make prediction. So people often prefer lasso, but the rich regression also is better in some specific examples. So here is one example that rich is better, and this is simulated example. and the many non-zero true parameters exist. So reach is expected to be better. And the left-hand side is just a conceptual graph. And actually, this is a simulation study. So we can decompose the entire error size. This is expected error size. And we can decompose it into the bias and variance. So this is the squared bias, and this is variance. So the variance gets smaller if lambda gets larger, because we have more simpler model. Lambda gets smaller, then more complicated model, the more larger parameters. So the variance gets larger, but the bias gets smaller because it's more flexible model. So at some point, the sum of these two quantities are minimized. So this is the best lambda. And in this case, actually, this dotted line is, okay, so this is expected the mean squared error, and dotted line is by ridge regression, and this solid line is by lasso. So ridge is consistently better than lasso. Yeah, actually, in terms of the bias, it's almost the same, but the variance, it's smaller for ridge in this specific example. Oh yeah, here, the R square on the training data. So R square is higher when model is more complicated. So lambda is smaller than the trainings the R square on training set is larger. And lambda is large, then simpler model. So R square is lower. And in this case, probably this simulation example satisfies n is less than p. So we have many parameters. So if we allow all models, then R square gets to 1. Yeah, so this is the other example in which the lasso is better. So an example with a few non-zero parameters. Suppose we have maybe 100 candidates of predictors, p is equal to 100, maybe n is, I don't know, 50, something. But actually the true number of parameters is 3 or something like that. Then, okay, so this is the actual optimal point. And with this lambda that we compare the expected mean squared error for this is ridge, and this is lasso. So in this case, the lasso performs better, much better. Actually, the optimal point are different, but the expected error is smallest here. And the dotted one, probably the best at here. So it's slightly different location, but yeah. So, but anyway, so it's much worse. So we have this difference. Sorry, the lambda is not determined. Sorry, the lambda is examined here, and also lambda is examined here. So lambda is large, lambda is large, or lambda is small. But anyway, so even if we choose the optimal lambda for each model, each of the lasso and ridge, that you can see the lasso regression performs better in this case. So it really depends on data that which method is better. Yeah, so some people think about the optimizing RSS plus lambda times j is equal to 1 to p beta j to the power some q or something, and the q is any number or something. And this optimization problem is more difficult to solve if q is less than 1 or more than 2. And the q is between 1 and 2. Usually the estimation isn't that difficult, and it can be done, but usually it isn't worth investigating this. Usually the q is equal to 1 or 2. That sounds fine. And if you use 1.3, maybe it's slightly better than the both of the methods, but they are not significantly better in most applications. So people just use lasso and rich regression. Also, probably people don't want to write the, actually the R code is pretty general. So you can change the Q value between 1 and 2, but usually it's not very helpful. Yeah, and this is the one example of lasso estimation, to see the characteristics of lasso estimate and rich estimate. So consider a simple model. Yj is equal to beta j plus epsilon j. So there are n parameters, and suppose that we have n observations. So the Yj is equal to beta j, so that we have the same number of parameters as sample size. So if we estimate this by OLS, trivially the beta j hat is equal to Yj, and the epsilon j is equal to 0 for all j. So this is the OLS estimate, least square estimate. But how about lasso and rich? So lasso and rich, they penalize the size of beta j. So beta j shrinks to 0. And here is the estimate. So least square methods, depending on the value Yj, the beta j is determined. So this is the beta j hat. So beta j hat and Yj is the same. You can see this is 1.5, then this is 1.5. So just this is, y is equal to x. Yj is equal to beta j's hat. But the rich regression, the shrinks to 0. So you can see that this shrinks towards 0. So slight difference. If lambda is larger, then we have the straight line like this. So it still goes to the center, but so this is for large lambda. So rich with large lambda, this. So it's a kind of uniformly the shrinks to 0. Not uniformly, just we multiply some constant. Yeah. And here the lasso estimate for beta j. So dotted line is the baseline, so least square estimate. So this is Yj is equal to beta j. And the lasso estimation basically have just the same distance from here. So just parallel shift. And within some interval, in this case, maybe negative 0.5 to 0.5. So it becomes 0. So parameter becomes 0. Yes. So yeah. So basically, we have large penalty on the size of parameter, but the RSS doesn't change much. So here the beta j hat is equal to 0. So this is the lasso. So this gives another explanation why the lasso has more non-zero coefficients. So within some interval, the coefficients shrinks to 0. And other points, it shrinks towards 0 with the constant amount. So yeah, this may be another reason. So this is another reason that the lasso is popular. So suppose that the estimate, the Yj, so Yj is large, like the Yj is 10 or something. Then beta j hat is what? The beta j hat is probably 9.5 because this is parallel. So the difference between these two is always 0.5. So it's not that large. But the rich regression, even small difference, if Yj is equal to 10, probably even with this, maybe beta j hat is equal to 8 or something. So the discrepancy gets larger. So this is another positive aspect of lasso. So again, which model is better? It depends on the example, but we have the both lasso and rich have bias, and the bias is, basically there are constant times this yj value for rich, but the lasso we have just constant shift. Any questions?
No.
So this, yeah.
That was a no.
No, okay. Okay, so and lasso and rich regression. Okay, so it's natural to penalize the size of beta. It makes sense, right? So if we have multicollinearity and we have very large coefficients, that's a problem. Suppose that we have the true model, the y is equal to, 1 times x1 plus 2 times x2 plus epsilon, and x1 and x2 are very similar, but this is true model, suppose. Then if our estimate is y is equal to, for example, the 100x1 minus 97x2, if x1 and x2 are very similar, actually this value and this value are similar, but the large coefficient makes prediction unstable if x1 and x2 has measurement error. So it makes sense to penalize the size of parameter. But also we can give the Bayesian interpretation of rich and lasso. So we specifically give mathematical explanation for lambda times the summation of beta j square, or lambda times summation of absolute value of beta j. And here is the theory. And you can see this one, summation of beta j square. So this is a kind of similar to, least square loss function. So we minimize the sum of squared residuals. And in least square, we minimize the sum of squared residuals because if epsilon I follows the normal, the 0 sigma square, then the likelihood function, to be concrete, the log of likelihood function of epsilon I is proportional to epsilon I square. Log of likelihood function, so negative epsilon I square. So that means that we can see this rich penalty as, penalty on random variable beta j. So suppose beta j is random. Beta j is normal 0 sigma square. Then the penalty is, the likelihood is negative epsilon I square. So the penalty is the negative of that. Right? So the likelihood larger is better. So larger is better. So if we take the negative of the negative log likelihood function, that becomes basically beta j square. So basically this rich penalty can be seen as the penalty on random variable beta j. So beta j is penalized if its size is large. So that means that we assume that the beta j is somewhere close to 0. If beta j is very large, then we penalize it. Or beta j is very large negative value, we penalize it. And the lambda is a kind of function of the variance of beta. Yeah, I don't discuss it, but to be exact, the negative log likelihood is equal to, I think the sigma square, 2 times sigma square and beta j square. So beta j square over 2 times sigma square. So the negative log likelihood, so this one. So maybe plus some constant, but basically 1 over 2 sigma square corresponds to lambda. So if sigma is large, then penalty is small. So sigma is large, that means beta j may not be very close to 0. So in such a case, we don't penalize beta j much. So this is pretty reasonable model in terms of Bayesian statistics. So we are penalizing this one, but that is equivalent to maximizing likelihood for beta J. And lasso, how about lasso? Lasso that minimizes this, and this corresponds to the situation that the beta J is random and it follows double exponential or Laplace distribution with center 0 and the some parameter, some variance parameter. Yeah. So maybe to be exact, that we assume that the prior distribution of beta, prior distribution of beta J is this. This is for rich regression, and this is for lasso. So in rich regression, the beta just follows normal distribution. And in lasso regression, that we assume the beta J is likely to be very close to 0 most of the time, but with some heavier tail here. Yeah, so in this sense, maybe the rich is more natural, because we assume that the beta J follows normal distribution, and lasso assume the beta J follows this distribution. In traditional regression model, of course, beta J is deterministic, so we don't consider the distribution of beta J. But in Bayesian statistics, all parameters also have prior distribution. So prior distribution of beta J follows this distribution, or this distribution. So in this sense, the lasso penalty and the rich penalty, the loss function of lasso and rich, rich regression, our loss function is RSS plus the lambda times summation of beta J square. This is entirely the negative log likelihood function we can interpret. And for lasso, also this is RSS plus lambda times summation of beta J absolute value. So this is again the negative log likelihood function, if we consider the Bayesian estimation of parameters. Yeah. Oh, have you studied Bayesian statistics before? Maybe no.
Your class, 5700, just a little bit.
Okay, so Bayesian statistics. Bayesian statistics is actually this is one good example of Bayesian statistics. But in Bayesian statistics, the beta J also follows the some prior distribution. So maybe I have to explain somewhere. Yeah. Bayesian statistics means that we have some prior information on parameter, for example, beta J. So beta J follows, for example, normal 0, the 1. And this is the so-called prior distribution. So I would say the density is f of beta J. So this is prior distribution. And the after a given data, so suppose X is data set, maybe more generally, maybe we have maybe Z is data set. Maybe Z consists of the X values and Y values of the so Z is the entire data of the predictors and response. Then we calculate the posterior distribution. So that is the conditional distribution of beta J given the data Z. by using the sum algebra, so-called Bayes rule. Then you can get the distribution of beta j. So distribution of beta j is like this. So this is the y is equal to the f of beta j given z. So we have the prior distribution like this, maybe normal distribution. So this is f of beta j. So in Bayesian statistics scheme, that we update this distribution by data. So originally, we believe that the beta j follows this distribution, but given some information, we have more specific information, so we can narrow down the parameter value. So that is the another scheme of the statistical estimation. So the point is that we have some prior assumption. So beta f of beta j follows normal the 0, 1 square. So it affects these estimates. Okay? This, the estimated distribution of beta j. In usual, frequentist statistics, the classic statistics, we assume that beta j is just a constant, and we estimate the beta j. So we have the variability of beta j. So it's actually implicitly we assume some distribution of beta j hat, right? So in frequentist statistics, so we have only the beta j is originally constant, but just unknown. And we estimate beta j hat. And the beta j hat is random. So it has some distribution. So frequentist statistics, that we don't have any prior information, any prior assumption. But the Bayesian statistics, we have some assumption. So in this case, maybe the assumption is beta j is around 0. It doesn't have a large value. Beta j is equal to 5 or 10. It's very unlikely. Beta j is equal to -5 or -10. Also very unlikely. So beta j is somewhere in between, maybe -3 to 3. Frequentist approach, the beta j can take any value before observing data. After observing data, we can estimate beta j hat. So it is based on less assumptions. Yeah. But anyway, so this is not really the focus of this section. So just the I would like to give you some idea that the rich regression and lasso can be interpreted as the Bayesian estimators, Bayesian statistics. Okay, so next one, so the tuning parameter lambda. This is optimized by cross-validation. So yeah. So sometimes, okay, so one example is that we have the data set and we divide it into training set and test set. So training set and test set, we use the validation approach. Oh, sorry, maybe I think this is too complicated beforehand. So just the most fundamental example. So yeah. So just this is data set. And we split this into several pieces, maybe just for simplicity, maybe 3. And we can use the cross validation to optimize lambda. So for each value of lambda, for each possible value of lambda, that we train the model with this data set, and we test the model with this data set. Then we can see which lambda performs, which lambda achieves the best, the smallest, the cross-validated mean square error. So finally, that we get the graph that the lambda, okay, so lambda value is, okay, 0.1, 1, and 10, and 100. Then you can get the cross-validated MSE. Then that value may be like this, and like this, and this, and maybe like this. Then you can see that the lambda is equal to 10 is the best parameter we can choose. So this is the way to determine lambda. So lambda hat. But sometimes we want to evaluate the expected error size. But if we use cross-validation to choose lambda, we cannot really calculate expected mean square error by cross-validation. So in such a case, we have to go the two-step approach. So maybe we divide original data set. Suppose we have original data set here. And suppose, for example, we can get the training set and the test set for test to know expected MSE. So in such a case that we have to use this training set, we have to divide this training set into several pieces and use a kind of the sub-training set and a sub-test set, and we optimize lambda here. So optimize lambda with this data set. By cross-validation, then use this to evaluate expected value of MSE. Yeah, so we have to do two steps. This is, okay, so choosing lambda by cross-validation, then calculating expected MSE by validation set approach. But maybe sometimes we do 2 layers of cross-validation. So if we want to test the expected MSE by the cross-validation, maybe you can at first prepare 4 subsets, 1, 2, 3, 4. Then we use 3 to optimize lambda. I think it's a little bit it's a little bit complicated. I think probably yeah, I don't know. Yeah, if we divide it 4 data sets, then use 3 of them to optimize lambda. Yeah, but that isn't really cross-validation, so lambda. Yeah, I think that we have to consider 2 layers of cross-validation. So in such a case, lambda. Yeah, I think it's pretty complicated. Yeah, so we have to determine lambda first, right? So we have to determine lambda first. So we need some training set. Then after that, we can do test set. Yeah. Yeah, if we use these 4 data sets, 4 subsets to do twofold cross-validation, it's a little bit complicated. We use 3 of them to train, to determine lambda. Then we use that lambda to evaluate the test set. And we choose another 3 subsets. Then we optimize lambda in a different way. I mean, in the same way, but we got the different lambda. Then we use the other data set for test. So it's pretty complicated procedure. So I don't know what's the best way, but the point is that we need the 2 layers of cross-validation or validation approach if we have lambda. So it's a kind of complicated. Yes. And here, sorry, here is an example of the estimate of lambda. And here, I think that this is the lambda value, and this is cross-validated error. So we can see that this point is optimal, so lambda hat. So cross-validated error is smallest. And this is the coefficients, so beta j hat. So the lambda is here, so it's optimal. So the estimated coefficients are here. Maybe many of the coefficients are equal to 0. And I don't know. Yeah. Sorry, I think this is a little bit confusing. So left and right, but we only have one graph. So yeah. Sorry. I don't know if this is for Rich or Lasso, but the anyway, so in either way that we have this graph and the lambda is equal to this lambda hat, that we have optimized parameters. Okay, so this is 6.2. Do you have any questions? Okay, so now I go to lab session. So lab 2. So yeah, so this is the implementation of lasso and rich regression. So first, the library, the ISLR, this is basically for data. So we are using this, the hitters data from the baseball, And the library GLMNet. So this is for fitting lasso and rich regression. So you have to download this and install this. And okay, so data set we are using is this hitters data, and hitters data is here. So basically we want to predict the salary of baseball players by several performance measures. I think that we have maybe 19 measures of the baseball players, batters. And at first, we remove the NAs. So we remove lines with at least one NAs. So this data set doesn't have many zeros, so it is possible. So if we have too many zeros, maybe we have to do some imputation. NA.omit function. So this is a convenient function. Then we want to fit the Y on X. So at first, we have to prepare the model matrix. So that is in linear regression, we have matrix form. The Y is equal to X beta plus epsilon. So this X is called model matrix. So model matrix of this salary data, the hitters data set. And yes, so yeah, so it's a little bit strange format, but the basically the salary is the response variable, and the other variables are predictor variables, and this is the data set we are using. So basically, we remove salary, but we take all the other variables as X, so predictors. So all remaining 19 variables plus intercept, that is this model matrix. So model matrix is probably the 263 by 20. 20 variables minus salary plus intercept. And this is for lambda. We have to optimize lambda value. So we choose these 13 values. We try those 13 values from 1/100, so 0.01, 0.1, 1, 10, up to 10 to the power 10. So usually for lambda, the small difference doesn't really matter. So lambda is equal to 3 and lambda is equal to 4. So the difference is very small. So we take exponential scale to see what's the appropriate lambda. And here is the estimated coefficients. So this is L1 norm. So this is a different. So this is the translated version. So this is the summation of beta j. Summation of the absolute value of beta j. So this is larger, then that means basically the lambda is smaller. And this direction, lambda is larger. Then these are estimates. Yeah, so actually I cannot really see the correspondence between this, the lambda value and these points. Then we see these coefficients. So we have tried the lambda is equal to 0.01. This has largest coefficients, and lambda is equal to 10 to the power 10. So these should have very small coefficients. And this corresponds to, the first column corresponds to 10 to the power 10. So actually the most coefficients are 0. And next one is 10 to the power 9. So this is, yeah, again, almost 0. So actually the 0, 0, and maybe 10 to the power 8, 7, 6. Then finally, we have some non-zero coefficients. Then 10 to the power 5, 4, 3, 2. And I think that we don't have enough, space to put it. So, oh, actually, below here we have, yeah. So, I'm not exactly sure. Oh, yes, yeah. So this is 10, and this is 1, this is 0.1, and this is 0.01. So you can see the coefficients. So with lambda is equal to 0.01, we have pretty large coefficients, all large coefficients. Yeah, for example, maybe the last one, negative 26.33. And here is 0. Yeah. This. And we want to take the, yeah. So this is a little bit strange because we input the 0.01 first, but actually this is in reverse order. I don't know, maybe the larger lambda is chosen first, or I don't know exact algorithm, but it will be reversed. And yes, so given lambda value, we get this RS, the coefficient sum of squares, so summation of beta j hat square. And given lambda value is smaller, then coefficient, the sum of the beta j's hat square is larger. Yeah, and finally, yeah, and yeah, so if lambda is equal to 0, then we get some parameter which s is equal to 50. Oh, yeah, that's true. And this s is equal to 50 means there's a parameterization. So we give lambda is equal to 10,000, then we get this value equal to 52, and this is s. So s is equal to 50 almost corresponds to lambda is equal to 10,000. So we get estimates given s here again. Yeah, so now that we want to optimize lambda. So we have just done the one estimation of ridge regression. actually maybe the 13 estimation for the different value of lambda. But now we want to optimize lambda. Oh, sorry, before that we do prediction. We do prediction. No. Sorry, now that we want to optimize lambda. And at first we want to calculate the total sum of squares. So that is the summation of the yi hat minus the yi, the y bar. So entire average. And square summation I is equal to 1 to n. So this is the maximum possible RSS. So if we only have the intercept, then the RSS is this value. So this is maximum possible RSS. So this value is the 220,000. And if we give the S, then we get the test error size of this. So this is the 142,000. So about maybe 30% smaller than the maximum possible RSS, that is called total variance. So now we want to optimize the lambda. And this is actually done by automatic procedure, the cv.glmnet. So by cross-validation, we do calculation. So we calculate the expected mean square error. So cross-validated the mean square error by value of lambda. And here, this is actually optimal lambda. And here, just the largest lambda within one standard deviation of the best one. So I would say that the one standard deviation is this band, sorry. And one standard deviation here. So actually this is the intercept. Sorry, maybe location is a little off, but like this. Okay. So practically, sometimes simpler model is better if model performance does not change much. So this is the lambda, so maximum lambda, which gives the best MSE plus minus one standard deviation of MSE. So anyway, so this is the optimal lambda. And optimal lambda is 25. So here the log of lambda is given. So log of 25.52 is about 3 point something. I think I calculated this before. 3.224. So this 3.24 is given here. So this value is 3.24. And with this, you can calculate the cross-validated error, and that is the 113,000. So the maximum possible error size is about 220,000, so about 50% reduction. So the predictors explains 50% of variability in Y. And this is the estimation result with the best lambda. Oh, alpha is equal to 0 means just the rich regression. Alpha is equal to 1. This is lasso. So that means that this alpha is characterized by the beta j to the power 2 minus alpha. Okay. So if the loss function is this, then yeah, so alpha is given, then loss function is this. So in this way, we can find the best lambda and the best model. And using these coefficients, you can do anything. You can also calculate predicted value for test data set and so on. And the lasso that we have similar format. We put the predictor values and also test values in this glmnet function, and given alpha is equal to 1. So this is for lasso. Then also we can give the grid to get the parameters. You can see, I think the some parameters are 0 here, and only a few non-zero parameters. We have 19 variables, but only maybe 3 are much different from 0, and only maybe a few of them are somewhat positive or negative, but mostly these are about 0. So this is again the same one. So this is the best lambda. So best maybe the log of lambda hat, and this is the maximum lambda hat, which is within one standard deviation of this lambda, log of lambda hat. So this is the lambda, which gives the MSE at least within one standard deviation of best MSE. And here the best lambda is 1.84, and the log of 1.84 is about 0.62, 0.621. So this is about 0.61. And which lambda minimizes? So yeah, so this is the lambda. Yeah, so just this one. So what the index of observations for each CV was minimized. So yeah, so we just want to derive this value, and that is the 113,000. So I think that this is similar to rich regression result. Rich regression best cross-validated the mean error. So mean square, I think the mean square error. So mean square error is the 113, but here the 113,581. So I think this is slightly smaller than error by rich regression, 113,880. So 113,880. So this is the expected cross-validated the mean square error by rich, and this is by lasso. So in this case, lasso is marginally better, and lasso estimates if we calculate, then actually some coefficients are 0 because the lasso makes some coefficients 0. So in this case, lasso is maybe marginally better than rich regression. That is the result. Sorry, we don't have enough time to discuss the exercise, but maybe we. Yeah, so I may now share screen, and yeah, maybe next time we do some exercise, but maybe I briefly discuss the exercise question. Oh, sorry. Yeah. And do you have any questions so far? So this is
does that get put out?
Sorry?
Has this been put into the modules or something?
Yes, under module exercise and exercise the February 22. So I think exercise 0222. And you can find this one and also the dataset. Dataset is abalone.zip. So that includes the 2 Abalone datasets. So Abalone datasets consist of 4,175 observations of abalones. And this is originally from the UC Irvine, the machine learning repository, but I removed 2 outliers. And that is the Avalon 1 dataset. And we have the response variable y, and we have some predictors x1 to x9. And the problem is here the problem is how to explain y by other ones. And y is the number of rings in Avalon. And the other predictors are just the size and also the gender, not gender, sex of this Avalon. So female or male, or I think unidentified. So we have the 3 genders. So we have the indicator variable for female, indicator variable for male, and length and diameter, and height and weight, and the shaft weight, and the visceral weight, and the shell weight, and so on. And obviously, we have difference in dimension. For example, the diameter is 1-dimensional quantity, but the weight is 3-dimensional quantity. So assuming that the the dimensions are different. So we consider also the quadratic term and the cubic term of these variables. Then we want to find the best model among the this kind of models. So so in statistically speaking, that we consider the 3-way interactions of these predictors, and we consider any linear combination of predictors to explain y. So one example is here. So y is equal to beta naught, beta 1 x1, and like the quadratic term here. I mean the interaction, 2-way interaction term here, and 3-way interaction term here, and also like cubic term or quadratic term or square times x1 square times x2 and so on. And so that is the exercise, but I think that today we don't have enough time. So next time that we will do this exercise. Do you have any questions?
Not at this point. Thank you.
Okay, so I will assign the midterm, take-home midterm today or tomorrow. So and you can submit by Friday next week. So see you next Monday.